Okay, I'm back on the last page here. Had a slight battery malfunction and a brain hiccup, but I've got this partly done here. Let me talk you through it. We're solving for x. This is a radical. So in order to do this, we have to isolate that radical and get it by itself. So I work from the outside towards my radical on the inside, and I subtract 1 from both sides. That makes it negative 85. And then I'm going to divide by negative 5 to get that radical alone. So when I divide by negative 5, I get just the radical. When I divide 10 by negative 5, I get negative 2x. And then when I divide negative 85 by negative 5, I get 17. Once I've got the radical, then I just square both sides. And when I square this, I brought it up here, and I just FOILed it. So there it is. It's multiplying by itself. The numbers aren't small. It's not very pretty. I'll try to give you easier, nicer numbers on the test, but it's okay to be challenged a little bit. Negative 2x times a negative 2x, positive 4x squared. And then I do the rainbow part, so that's 17 and 17. Sorry, 17 times 2, that's negative 34. Doubled is negative 68. And 17 times 17 is 289. And then when I square that radical, I get just the 10x minus 1 that was inside the radical. Now that it's a quadratic, this goes to that section in the book on quadratics. I move everything over to one side, set it equal to 0. I add 1, the 289 goes to 290. I add 10x, the negative 68, sorry, I subtract 10x, got to be careful, and I go from negative 68 to negative 78. And then I see that these are all even, so I divide everything by 2 just to make it simpler. However, if at this stage you just put it into quad form on your calculator, you're going to be fine. So I would recommend you have that. You can find it on the website, on the Moodle site. I divide everything by 2 though, and then I can at least try to factor it, and with a little guess and check I did factor it. It's 2x minus 29, x minus 5. Really the only way you're going to factor 145 is either 1 and 145 or 5 and 29, because 29 is prime. So it actually does factor pretty easily. Then this is equal to 0 when x equals 5, and this is equal to 0 when x is equal to 2 over 29, or sorry, 29 over 2. So that's the other 29 halves. So it's important to get both solutions. If I plug 5 in up here, you'll see that it does in fact work. And I'll let you maybe plug in 29 over 2 if you're curious. If it doesn't work though, then you cross it out. And sometimes these radicals, they look like they have a solution, but in fact they don't. So you want to be careful. This next one, it's very crowded here, but I've got this function g of x, I've got this function f of x. Find f of g of 2. Well, I just plug in 2 for x here. 2 squared is 4. 4 times 4 is 16. Minus 10, that gives me 6. So this equals 6 for g of 2. Then I find f of 6, and I go here. 6 times 2 is 12. 12 minus 3 is 9. The square root of 9 is 3. So that's my final answer. I shouldn't confuse you there. And then finally, this is just the algebra of subbing in f of x in place right here. So I take g of x, g of f of x is going to be 4 times, there's x squared minus 10, and in place of x, I replace that f of x, which is radical 2x minus 3. Well, when I square that, the radical goes away, and it's equal to 4 times 2x minus 3 minus 10, and that's equal to 8x minus 8 minus 12. I can multiply. 4 times negative 3 is negative 12 minus 10, and my final answer here is 8x minus 22. All right? So that's that solution. In the home stretch here, graph this absolute value. I think I told you in class that the easiest thing is to really find this vertex, and if it is x plus 2, a normal absolute value function goes like this, with this vertex at the origin. That's when you have f of x just equal to the absolute value of x. I think it's quite easy to just look at that and say, well, when is this equal to 0? It's when x is negative 2, so this will move to the vertex being somewhere along this axis of symmetry, x equals negative 2. Then I just plug in negative 2, and that becomes 0, and that becomes 0, and I'm at 1. So the vertex moves to 2, 1. And then after that, just plot one other point and make it symmetrical. I think the easiest point is along the x-axis or the y-axis. When x is 0, I get absolute value of 2 is 2. 2 times negative 4 is negative 8, plus 1 then is negative 7. So it's going to be down here. Let's just call that negative 5, negative 6, negative 7. So it goes down like that, and then it'll be symmetrical. If that's 0, negative 7, and this is 2, 1, then this is going to be 2 units over here, so that's going to be negative 4, comma, negative 7. And there's my graph. Okay. Sometimes you do a rough draft, and if you really are uncomfortable drawing it like that, you can redraw it always and just, relabel it and get it like that. But I would accept that. That is fine. Okay. Here finally it says if 3 is a 0, find the remaining zeros. If 3 is a 0, find the remaining zeros of the following function. All right, this is the little unit we tacked on about polynomial long division. If 3 is a 0, we know that x minus 3 has got to be a factor of this, because when I plug in 3, I get 0. All right, this is the little trick. So if I put this right here and write 2x to the third minus 9x squared minus 26x minus 21, and then I start this polynomial long division, I ask myself, what do I need to multiply right here to get exactly 2x to the third? Well, that's just a plain old x, so if I multiply by 2x squared, that when I multiply will give me that. I need to multiply into the negative 3, and I get minus 6x squared. Okay? You can subtract here if you want, or you can change the signs and add, and I find that easier. That becomes 0. That is just negative 3x squared. Bring down this minus 26x and repeat the process. I multiply x by negative 3x to give me negative 3x squared. Okay? Then I multiply negative 3x times negative 3 and I get plus 9x. When I add that, I'll change the signs, and it's negative then, and I'll add and I'll get minus 35x. Bring that down, minus 21, and now I will multiply this by something, and that doesn't work. Darn nation. Oh well.